So this is day 2. Staggeringly, we are on to day 2 of the International Science School, and it's time for our second speaker. And our second speaker is from the University of Swinburne, which is down south, down in Melbourne. He is the Pro-Vice-Chancellor, which is an impressive term, for Flagship Innovations, which is an even more impressive term. And if you want to know what that means, you can ask him later, because it's a very impressive title that would look very good on a name badge at a drinks event. But he can explain to you exactly what that means. Most importantly, he's here to talk to us about one of the most fascinating things in the universe. It makes up a ridiculous proportion of the stuff in the universe. We've known about it for a really long time, and we still don't know what it is, which is dark matter. So would you please make very, very welcome from the ARC Center for Excellence for Dark Matter Particle Physics, Professor Alan Duffy.
Thank you. Thank you. Thank you all so much. It is an absolute privilege to be here. I am going to do my best to give you a whistle-stop tour of the reason that I am so confident, and my peers in this field, that there is an invisible stuff that outweighs everything we can see 5 times over, that you have never smelt, tasted, touched, seen. Indeed, you owe your very existence to it, and yet we don't know what it is. But we are incredibly confident about the fact that we don't exactly know what it is, but we know everything else very well, okay? So bear with me, and hopefully you'll be convinced in this lecture and the next. Before I begin, I'd like to acknowledge the traditional custodians of the land in which we're meeting, the Gadigal people of the Eora Nation. I want to pay my respects to elders past, present, and emerging, extend those respects to any Aboriginal and Torres Strait Islander peoples who may be with us today. Before I talk about the invisible universe, let's have a quick census check on what we can see. Who knows what this spacecraft is? Excellent. This is the successor to the Hubble Space Telescope. It is sitting about 1.5 million kilometers from us. The data from this spacecraft streams, in fact, down via Swinburne, our supercomputer at OzStar, and we are the node that serves up the data products to the APAC region. So, in a program led by Professor Carl Glazebrook, this has a sun shield that is about the size of a tennis court. The 6-meter, give or take, gold mirror, or gold surfaced mirror, is so ginormous because it is collecting very long wavelength light, or known as infrared, so going past redder than red, you get to infrared. And the, enormous mirror can capture the long wavelength light very sensitively, but it can also provide a resolution similar to Hubble, which is actually tiny. It's about only 1 meter across the actual mirror. With the JWST, oh my God. Okay, that's cool. We can see images like this. Who knows what this is? Shout it out. Nebula, yep. Does anyone know specifically the nebula? Yes, very good. So this is a star-forming region. So stars like our sun formed in ginormous clouds of gas and dust, pulled together by the gravity of all that material, getting ever denser, ever higher pressure, ever hotter temperatures, until you get the talk that you saw yesterday when fusion is triggered and a star is born. And then from the light and the radiation from that reaction, it destroys the environment that it formed within. This is not working. Okay. So that's fine. I will just have to hang around here.
For the time being, I'm really sorry.
That's all good. So, and in fact, we can see some newly formed stars revealed in this image that have destroyed the nebula that gave them life. Now, if we zoom out, those collections of stars and gas, of course, form structures known as what? Galaxies. That was a very uncertain one person said that. Okay, I'm scared for where we're about to go in terms of the level of detail in astronomy and physics. Oh, goodness. I assume you were just shy and you all actually knew that, right? Excellent. Those dust lanes now we're seeing on a much larger scale. That is the silhouette, backlit by, in this instance, about 100 billion stars. And then if we take JWST and we point it at a region of empty sky, at least to our eyes, and open the aperture in a very non-physics sense, we eventually collect photons of light and we see this image. Now this is the deep field, first captured by Hubble. These are all galaxies stretching back as far as the eye, or in this case, far more powerfully, the JWST, can see. Close to us, we can make out the galaxies and their shapes. The very much more distant dots that look like stars are, of course, just very, very far away galaxies, and we're seeing them back as they were when the light left. So we are seeing back in time. And essentially, we're seeing some of the first galaxies ever formed. Because all of those fit within a patch about the size of your thumbnail stretched out at arm's length, you can imagine how many little thumbs up you can give the entire sky. So when you multiply that number of stars in our galaxy and that number of galaxies, each of which contain about the same amount of stars, 100 billion or so, about 10,000 galaxies in that patch, and then the number of patches across the entire sky, you get an absurd number of several trillions of galaxies, of which each contain hundreds of billions of stars, and at least as much, again, material waiting to yet form stars. All of that stuff is outweighed 5 times over by an invisible dark side to those galaxies. That is what I'm going to try and convince you of in our time today. So, cosmology. Who knows what it is? I tried this earlier with a few select subsample. Show of hands, who's heard of... Hey? Study of the universe. Do I have any other advances on that? Study of the cosmos. Very good. Anyone else? Study of galaxies. Yep. Yep. Physics on the scale of... Well, interestingly, physics, I've just noticed there's a lot of spitballs up there. That is weird. Can anyone else see that? Yeah. How gross is that? University, Sydney. Wouldn't happen in my uni. All right, the study. The study of the universe on large scales. And that allows us to simplify some of the physics, as we will do in a little bit. Why? It's because we're actually interested in the origin, the evolution, and ultimately the fate of the universe. That is the audacity of the field of cosmology. To misquote Douglas Adams, it's not much about life, mostly it's the universe and everything in it. So, cosmology is the study of the universe on the large scales, where you can simplify the complexities of a galaxy with a point of light. That is what I did my PhD in. However, I've since become extremely interested in those points of light and have realized that you actually can't learn anything about the universe until you know everything else within it. So, what's in it? Well, we're going to zoom out in this video. Essentially, this is the powers of 10. So we'll essentially every few seconds zoom out another factor 10. So we're seeing the Earth and then the moon, well, zoomed out past the moon. We're seeing the inner solar system, taking a few hours to get signals across to the gas giants, and then eventually out to many years when we get to our closest neighbor, which is a very long time. I feel like that just missed an entire section of stars. But anyways, now we have a galaxy which is about 100,000 light years across. Of course, this is the Milky Way. And we'll keep zooming out until the galaxy, the very points become points of light. And those points of light are collections of a much larger structure known as the cosmic web. And all of this becomes essentially the realm of cosmology, where we are now interested in the behavior, the shape of the universe, etc., on these large scales. And now these colors indicate overdense regions, and it's not random, it's not evenly spread out. It's clumped, it's forming structures, and we'll get to that in a little bit. All right, so What do we know about the universe? Well, we know it's expanding, indeed accelerating in its expansion thanks to Brian Schmidt, who has doomed us all with that discovery. I won't get to that in this lecture. The universe is, I needed to update that number. We just shaved the age off by 800 million years. The universe is flat, we'll get to that. And the universe is comprised of three main things today: baryons, which is the fancy term for atoms, essentially you, me, stars, planets, gas, the periodic table, essentially. 5 times more is dark matter. So roughly speaking, a quarter of the universe is matter of some kind, be it dark matter, which we'll get to, or baryons. And then 3/4 is dark energy, which is driving the accelerated expansion of the universe, of which I will say nothing. Because this is a talk about the dark matter. But get Brian to give a talk about dark energy sometime. It's fun. We actually know very little about it, by the way. That's also the other reason I'm not speaking. It's there. It seems to be the cosmological constant. We can talk about it at lunch. Critically, I want us to go through why how we know these facts. So the first step is to understand spectra. So we have, in this incredible animation I'm very proud of, if we get a high energy photon of light, so something in the blue, and well, indeed, actually, ultraviolet, and it hits the electron, it raises the energy of the electron to a higher shell, which spontaneously will relax, emitting a photon of light, and then again fall down to the next shell level, emitting another photon of light. Each of those photons are a very specific color, that is to say energy, that is to say wavelength. We're all good with spectra? So how we know it's expanding is that the spectra provides us with the perfect ruler. So we have objects at rest, and the spectra in its light, these are absorption spectra, so the black regions indicate some atom which is absorbing. Essentially, its electrons are absorbing wavelengths of light at exactly that color in this instance. So let's just follow this. At rest, we then get an effect known as the Doppler shift, so familiar to us all, where we have an ambulance coming towards us, and its wavelength is compressed, so it's a higher pitch, so and then as it goes by, it's expanded, stretched out. Right. Again, Doppler shift, we're all good with. So as that's moving away from us at greater and greater speeds, the color appears to redden as it stretches away. If it comes towards us, it's the opposite, and the object appears bluer. How do you know it just wasn't intrinsically bluer or redder? Your spectra is actually shifting, so you know exactly. And that is exactly how Edwin Hubble discovered that the universe was expanding. Here is the actual image from his plot, where we have the velocity of the objects, soon to be called galaxies, I think at this time technically we're known as nebula, as a function of the distance that they are from us. Kilometers a second as a function of parsecs, which is about 3.26 light years. The key here is that everywhere you look, outside of just the initial location to us, the objects are moving apart. Now, if they're all moving apart, unless we are the literal center of the universe, it implies that everything is moving away from everything else. And that is, of course, the expansion of the universe. There's a very simple linear relation between the x and y, the y and x axis. Velocity equals h naught times the distance. So h naught in Hubble's honor is known as the Hubble constant. And it tells you how fast is a galaxy moving away from us as a function of that distance. So in other words, if you are twice as far, you are moving twice as fast from us. Hubble's law is a profoundly powerful tool because we can actually then use it to determine the age of the universe. Remember, this is the expansion rate. So going forwards in time, things are going away from us. What happens if you're going backwards in time? Right? Things are coming together. We'll get to that, obviously. This is the Big Bang, which I figured most of you are going to get to the ending on that. But we can define something called the Hubble time, which is literally the time it's taken for the things to get to the distance that they are. And because of that linear relationship, it is literally just 1 over that Hubble constant, which is very convenient. It's almost also true as well, which is helpful. It's not exactly, because things have slowed down slightly since the expansion began, but very, very close. So we actually can figure out from Hubble's expansion and the Hubble's law, in particular Hubble constant, the actual age of the universe itself, how long it has taken to get there, which is what I want you all to do now, but you didn't think this was coming. Here are some numbers. I've changed it into megalight years because parsecs is just, that's too painful. We don't have a whole heap of time because we've started like 30 minutes late. So I will set 1 minute frantically. Can you solve for h0 in this instance? And then 1 over that is the age of the universe. Go. How awful are the units going to be? Ugh. Two lines are depending on what samples you choose to fit. But with the scale of that, it's going to be, doesn't matter, yeah. This is cosmology. If we even get to a factor 2, we're feeling pretty good about the answer. Hey? What's that? I would go, just get it to 1 or 2 significant figures, right? That's enough, yeah. 1 is fine. Order of magnitude is fine. So the units of h0 are kilometers per second per megalight year, technically megaparsec, megalight year, and 1 over that will give you it in seconds. Kilometers and light years cancel. 1 light year is 10 to the 10 kilometers. It's 10, what did I say, 10 billion? Yeah, hang on, let's see. So, if the Hubble time is th, the observable universe is, that's the time light's had to get to us, so it's the speed of light times that. So, how big is the universe using Hubble's and how old? Let's go. Oop, that's insane. Why are none of those numbers appearing? Oh, okay. All right, that's sad. So, I will ask you all, who got me a number for h0 in kilometers per second per megalight year? What number? Okay, all right, well, I'll go back to you in a second then, because that's where I'm going to end. Yes? 161. Sorry, can everyone hear that? Oh, it's not me? Okay. 161.3 kilometers per second per megalight year? Yep. Yep. Any changes in 16? 160-ish? Yep. 151. I'm loving the accuracies on these. Yeah. Anyone over here? Yeah, 151. Excellent. Yes? Yes, very nice. Okay. So what I'm hearing is I would actually then take all of your individual answers and I would average, take the mean, and that would give me something almost exactly correct, which in that particular plot, as near as I could be bothered finding out, it was about 158. But that is literally the precision I could be bothered solving that. Because if you take the inverse of that, how old is the universe? Yeah, cool. All right, how many seconds? 200. Yeah, no, 2 times 10 to the power 9 seconds. 2 billion seconds? I think you might have said 2 billion years, by the way. I think you might be solving it in years. You said 19.8 billion years. It's a little high. It's actually, did anyone else have any other advances on that? It's tricky because seconds and years. Did anyone say something? Okay. If you solve it, you will get 2 billion years. 10 billion is 10 to the 9. Yeah, so you got, I think units are years. So if you plug that in, as Hubble did, you get that the answer is the age of the universe is 2 billion years old. Are we happy with that answer? No. That's right. The universe is also not 2 billion light years across because the Hubble constant is wrong, at least when Hubble solved it. He got the distances wrong. So today, we have a much better number, and this is work that my PhD student Mitchell Dixon has done using supernovae. These are the exploding stars, there we go, which you can use as a standard candle. Essentially, they're much further away, so they appear fainter, and hence you can solve that for that distance, and then, because you know exactly how bright they are, if they were right beside us, for example, and plot it against its redshift, you can get the expansion of the universe. Sadly, don't have time to do that today, but that gives us a number. The most recent number, at least, is about 75 kilometers a second. So not the 160, right? Rapid expansion that Hubble thought, because the objects he was thinking were, in fact, too close as a mistake. That was just a mistake he made in terms of the distance measures. If you put in now 75 kilometers per second per megaparsec, which you get 23 kilometers per second per mega light year, units are horrible in astronomy. 1 over that's Hubble time. That's 13 billion years is the latest number. And the observable universe is about, if you think the diameter is 26 billion light years. However, the universe has expanded since that period. So actually, technically, it's bigger again, but pretty good, right? From just that little single line, at least if you had the most recent corrected distances, you can actually measure the age of the universe to basically, 10%. Which is pretty cool. Now, the expansion, that took way too long, my goodness. All, of course, if you wind the clock back, originates at a point of increasing density until finally, wind the clock back, it's getting hotter and hotter and hotter, until the entire universe itself is so dense, it is akin to the density at the center of the star. So you're having nuclear fusion, this is called Big Bang nucleosynthesis, and you wind the clock back yet further, our physics breaks, and we call that the singularity, or the Big Bang. Here is the cartoon graphic. We can't be outside the expansion of the universe, of course, but this is what it looked like if you could, where you get this rapid inflation period. The universe is very, very hot and dense. Eventually, in fact, it begins to form atoms, so protons, neutrons, and electrons. Eventually, it gets cold enough that they can begin to combine, and we get this green-colored pattern, which I'll talk about in a second. And then, really, really boring for a few 100 million years as gravity is beginning to take over the collapse, forming those stars, helped by dark matter, which we'll get to very soon. And then finally, those stars switch on, and we transition from what's called the Dark Ages to the period of known as the epoch of reionization, and then all the stuff that follows. But I want us to focus on the cosmic microwave background because this is actually the best, most precise evidence for the existence of dark matter. So this, if you could look into the night sky with radio eyes, is what you would see. This is as seen by the Planck microwave satellite. It is orbiting in deeper space. It's actually close to JWST, in fact. So looking out across the entire sky as far as it could see, it gets this pattern. This is just what a sphere looks like when you project it onto a 2D map. So this is the globe. So now when you look at that, right, that's wrapping all around. That's the plane of the galaxy in the middle. Lots of clouds of gas. Very fascinating physics, but not cosmology. Instead, we want those little dots of light behind. So by witchcraft and wizardry, if you manage to pull out that stuff that's in the way, which we call lovingly the galaxy that we live in, behind it are these regions of brighter, hotter, and flip side, colder patches of the sky, seen as radio. It is the afterglow of the Big Bang that has since cooled to radio wavelengths. And these blotches hold a treasure trove of physics. This is what you're seeing. You can do the analysis, breaking up those blotches into essentially their size. So on the x-axis, we go from 10 to 1,000. This is a multipole, but essentially from big features to small, from big blobs to small blobs. And then the y-axis is how bright, so literally how the temperature of those, but how much of that map is made up of big blobs versus small blobs, right? Super precise physics here. Big blobs versus small blobs. Now, those ripples that you're seeing on the right are one of the most extraordinary bits of physics. We have, in the early universe, as I mentioned, a time when the temperature was so great that atoms could not exist. There were protons and there were free electrons. Sorry, is there a question? Yeah.
What is the relativity?
Sorry?
What is the relativity?
So on the left is the blotches that we're seeing from here, the cosmic microwave background. So you can analyze those blotches mathematically by creating the plot on the right, which is what we call a Fourier analysis, or essentially it's plot as a function of multipole, but essentially, as I said, you're going that curve, as you sweep through that line, you go, okay, I have a blob at 10, which is a big scale blob, going to higher numbers along that x-axis, which are increasingly small size blobs, right? So that is literally, when I look at the afterglow of the Big Bang, how many big blobs do I see versus small blobs? And the pattern is that line, that wiggly line. And I'm glad you asked, because this is really, really important. What's causing the wiggly line? What sets the blotchiness in the afterglow of the Big Bang? We have, as I mentioned, where the atoms, it's too hot for atoms to exist as bound. We have protons and electrons, and we have lots and lots of light. And what happens in the early universe, it's so dense that the light tries to travel, immediately hits an electron floating around, bounces off, hits another, bounces off, hits another. You can have a huge amount of material, and its gravity is trying to collapse. But as it does, the photons of light are bouncing around between, scattering, literally knocking the electrons back like a pressure. And in fact, it's like what happens in the star. The star is propped up by that photon pressure pushing back. The entire universe was like the center of a star. So as gravity tried to squeeze a big blob on the sky, just like a spring, the light within began to get ever more confined and pushed back, and it sprung out. And then it fell back in and sprung out. That was occurring over hundreds of thousands of years, entire vast regions of the universe, like an accordion. Just that is the sound waves, essentially, that we are seeing plotted in the wiggles. The exact structure of those wiggles can tell you about the shape of the universe. Oh, I really don't have time to do it now. We're so late. Oh gosh, it's such good physics. But we have to get into dark matter. Okay. If the universe is closed, by which I mean it expands, but there's so much gravity it pulls it back together. So in space-time, 4 dimensions, that closes, right? So that's what's happening, closes. We have a particular kind of a geometry where triangles inside angles of a triangle don't add up to 180. They are greater than that. If the universe is flat, then geometry holds, Euclidean geometry, so triangles add up to 180 degrees. And if the universe is open, it means it expands forever at an accelerating rate. There's just not enough stuff to close it. And at that point, angles of a triangle add up to less than 180 degrees. In other words, if you look to the sky, which is the top image, and you say, what size of angle, literally on the sky, are the blobs? Because I know them from physics. And that's the beauty of the CMB. We actually understand what the blobbiness should be. We can measure the geometry of the universe by how big those blobs are. Remember that angle piece I talked about? I'm so sorry, I don't have time to do the fun bit of that. Now, what I want to get to about the whole point of the cosmic background was these lines. On the right, we're changing the amount of stuff in the universe, and that wiggle, literally how bright are the blobs, big blobs versus small blobs, changes, and I hope you can see that. What we're doing on the right is going from a universe with 0.1, so 10% matter, up to, say, 50% matter, and we can see the change. If you change the amount of dark matter to baryons, you're changing that kind of spring, how strong does the spring push back, and again, you change the shape. So I just want you to be aware that from the picture of the microwave background, it looks beautiful. I mean, it truly is. But because we understand the physics of that time, we can literally measure the amount of material in the universe from just the way these ginormous universe-spanning sound waves pushed back and forth. This is the latest result, one of the latest results. If you're interested, if you look again with radio eyes on the sky, that first harmonic is at 1 degree. The moon is about half a degree, so it's about 2 full moons on the sky. You'll see blobs, more likely to be that size than anything else. We'll skip through that, lots of photon support, and we can figure out what the universe is comprised of based on those exact shape of those lines. Now, some of you, I hope, have realized that I introduced redshift, or the fact that things appear redder as they're moving faster away, or they're further away from us, so they appear to be moving faster away, and have immediately thought, oh my gosh, he's told me the Doppler shift explanation, which is clearly not right. It's an expanding universe. Hands up who thought that? No one? Someone? Oh, okay. All right. I kind of lied about the Doppler shift. These objects are not moving. The space in between us is expanding. Essentially, it's stretching out the wavelength of light. That's why it gets redder and redder and redder as it goes further away. Which is a wonderful Veritasium video. Grant Lewis of Sydney University, however, demonstrated really, really wonderfully that it's like a lot of infinitesimal, tiny, tiny, tiny Doppler shifts added together. So it's actually not a complete lie, but just so you're aware, if you go far enough away, Hubble's law, big enough distance, you will get a speed that's greater than the speed of light. Right? If d keeps getting bigger, v is going to get more than c, the speed of light. How can anything travel faster than light? It can't. But the overall distance between us is increasing faster. Even locally, it's just little bits, but little bits added together over a vast distance will give an overall expansion greater. All right. Now, physics. So we have Newtonian gravity, 2 masses together attract one another, as I hope you're all aware, proportional to their masses divided by the distance squared. That's fine for most instances of astronomy, in fact, but for cosmology, of course, we need something a little more advanced, which is Einstein's GR, where masses curve space-time and curved space-time tell masses how to move. And what we perceive as something going through a curved space looks like gravity has reached out to pull it. So the moon has been pulled around the Earth, but in fact, the moon was traveling straight all along, just through a curved space-time. There's the tensor. Don't have time to go into it. But that's, yeah, this is really too much. All right. Now, with a simulation that I do, a supercomputer simulation, you can start off just after the Big Bang. The universe is nice and smooth. You put in the stuff that you think it needs, the atoms, the baryons, which is in orange, and the blue, which is dark matter. And I've slightly offset the orange from blue so you can kind of see. Otherwise, it all looks, it sort of blurs out. So these blobs, I'll play this again. So we have this galaxy that's beginning to spin up. It's actually a little baby spiral galaxy. Lots of material around, lots of long streams or filaments of material. Here we are. So here's a lot of satellites around this galaxy. There's some little spiral arms, very cute. I feel very parental about that one. It's one of the first baby galaxies ever made. So again, the universe starts off smooth and then very quickly collapses, pulled by the gravity, in fact, of the dark matter, which begins to collapse first in the universe and gets a head start. And these blue structures, the dark matter, acts as a gravitational backbone around and within which the dark matter is accelerating the infall and then the growth of the galaxies. And that's what I meant by we owe our existence to it. If you don't put dark matter in, which I made a mistake and didn't do once in my simulations, nothing forms by the present day. You don't get galaxies in this amount of time in the universe. We need the dark matter to speed up the formation of galaxies. Its gravity is absolutely critical to pulling in the material. This ratio of visible to invisible material, as I mentioned before 5 times over, is weirdly the exact ratio of the visible extent of an iceberg above the waterline to that below the waterline. That is just numerology and has no physical insight. So now we get into one of the oldest proofs for dark matter, and that is the fact that galaxies appear to spin differently to what the visible material's gravity would indicate. As you go further away from the center where all the light and mass is, you would expect objects to move more slowly. But in fact, what we see is everything moves at the same speed. This is weird, and it was noted by Vera Rubin. So this is also known as weighing a galaxy. So Vera measured the velocity of the stars at one point going around a galaxy, a little further out, and a little further out. And she plotted that speed against the distance. And we're going to demonstrate this, if you'll indulge me, with this little physics demonstration. This is a high-tech bit of experimentation. It is not my child's toy. As I spin it around, slowly, there's a certain amount of force required to hold on. And then if I speed up that rotation, there's more force required to hold on. In fact, quite a lot more. Now, what if I extend the distance and the radius of that rotation and keep the speed up? There's even more force required. Now, if I don't have enough force holding onto the string, that's what happens. So if you can measure the speed at something going around and increasing distances, you can measure how much force is holding onto those objects. If there's not enough force, there's no strings in space, but there is gravity. If there's not enough gravity to hold on, then those objects should fly away just like the child toy. So that's what Vera decided to do, measure the speed of these distant objects around a galaxy. And what she found was instead of the bottom curve, so the fact that stuff close to all the gravity in the middle would be going fast, but then further out, you would need more force to hold on to those stars, and essentially they would have fled the galaxy. Instead, what she found was the speed just kept on going up. In other words, it was like the child's toy, where you've got objects going at incredible speeds at this incredible distance. What on earth is holding on? Where is all of this force, this gravity coming from? If there's lots of gravity, that means there's lots of mass. But she couldn't see it, and that's why it's dark. Mass, so there's matter there, has gravity, can't otherwise see it, dark. Astronomers are not particularly clever with naming conventions. It's that simple. If you like, you can actually figure out from this equation that the mass, this is just circular motion, it's nothing too fancy. If you plug in the numbers based on that plot, you will be able to weigh it, the galaxy. There's if anyone wants to take a picture of it, you're more than welcome. I think these slides get shared anyway. So what we discover is that the galaxy has this vast amount of otherwise invisible material, 5 times more than all of the stars and gas added together. But more than that, it also extends much further out. And in fact, what we see as the visible extent of the galaxy is this tip of the iceberg, and there's a ginormous dark structure that extends beyond. Today, we do these kinds of velocity maps, and we get stuff like this. This is literally a radio telescope. We can see all of the material moving at different speeds, and we can do the harmonics, so we can break down, just like we did the CMB maps. We can see what's the net rotation, so we see blue shift. This now is a Doppler shift. Material coming towards us, red shift going away. So that galaxy is spiraling literally towards us, almost seeing it edge on. And then you can remove that signal and see the rest, and you can start to get an understanding of how the material is moving within. I share this just so you know the kinds of data that you get today in astronomy. You can break that velocity diagram apart This is now velocity as a function of that distance. That's the total velocity, measured velocity. And then we can say, well, all the gas contributes this tiny little bit on the bottom, so not much of the gravity by the gas. The stars are pretty concentrated in the middle, so they can produce a lot of gravity and hold on to material near them, maybe 5, 10 kiloparsecs, but then much further out, essentially, all that's left that can provide this is this dark matter. So we infer the existence of dark matter by this unexpected motion where the visible material is pulled by the gravity of an unseen companion. Everyone happy with that? It could be that gravity's wrong. Ask me that over lunch. It's not. So, we have measured that the universe is expanding. It means that it came from a singularity, if you wind the clock back. I want you to think, though, is our galaxy expanding? Hopefully you now remember what fraction of the universe is dark matter. I'm hearing lots of different numbers. About a quarter of the universe is matter, of which about 4/5 is dark matter, and just 1/5 us is the atoms. So we are a tiny, tiny little bit. And what is that comprised of? We don't know, and we will get to that later on. Oops. And what we've been able to measure is that the extent of the dark matter continues for tens, if not perhaps even 100 times further out than the disk, the visible extent of the galaxies themselves. So we have this huge amount of, at this point, unexplained additional stuff, the gravity of which is the reason that our galaxy was able to form so quickly in the first place. And we will now begin to see that in the next lecture, but I think we will stop there. Thank you so much for this first lecture.